Today we will start a new chapter, that is system of particles and rotational motion. System of particles and rotational motion. System of particles and rotation. Okay. So first of all, we will discuss what is meant by particle. What is meant by particle? Particle means it is an object of finite mass and whose size and internal structure can be neglected. An object of finite mass. An object of finite mass and whose size and internal structure can be known. Whose size and internal structure can be neglected. Okay. It is known as particle. So, its size can be neglected. No need of worrying about structure, but it will have a definite mass. That is known as particle. Okay. Now, we can deal with system. What is meant by system? System is a collection of particles which mutually interact with each other. Which mutually interact with each other. So system, how can we define a system? It's a collection of particles. Many particles will be there and those particles will interact mutually with each other. That is known as system. Okay. And now internal forces. The forces which act inside the system between the particles is known as internal forces. Between the particles. The forces which come into play between the particles inside the system is known as internal forces. So, if we are considering a system, for example, we are considering a system which contains two particles, 1 and 2. Okay, two particles are there, 1 and 2. This is a system. So here we can say that this first object will exert force on second object. Same way, second object will force on first object. So these forces we can say that internal forces. So clearly we can conclude that net internal force on a system or of a system will be same. Okay. Now what is meant by external forces? Forces which act from outside the system. Forces which act from outside the system, that is known as external forces. Okay. So I think these four terms are clear to you. So why we are dealing with this? So far we consider, whenever we are considering motion of the object, we are considering that object as point object whose size is negligible. That can be considered as a point object, like that we are considering. So far whatever we have particles. But actually we know that whenever we are dealing with the object which are that we are seeing, it has definite size. It is a rigid body. So we have to consider the motion of those type of objects. That's why we are going to discuss that how it can be discussed or how we can implement those that we are going to discuss in this. For that, we should know these things. Okay, now we will discuss one more thing regarding that one, that is center of mass. So, center of mass of a system means it is the point at which the entire mass can be assumed to be concentrated. Is that the point at which the entire mass can be assumed to be concentrated. Concentrated for describing the translatory motion of the earth. What is meant by center of mass? Center of mass of a system, when we are considering large number of particles. So, center of mass of a system can be defined as the point at which the entire mass is assumed to be concentrated. So, we cannot find such a point. If you are checking, we cannot find such a point. But for our calculation and for writing down the equation, it will be easier. So, we can assume that the entire mass is concentrated at a point. And that point is known as center of mass. And what's the speciality of that center of mass? By knowing those points, it will be easier for the description of translatory motion. So, what is meant by translatory motion? Translatory motion means if the object is entirely moving from one position to another position. That is known as translatory motion. In rotational motion, what happens is that it will be fixed and it will be rotated. But in translatory motion, so if you are an object is there, if you are exerting force, the entire object is shifted from here to here. So what happens? We can say this is an example of a translatory motion. So the entire body will be moved from one position to another position. Such type of motion is known as translatory motion. So for translatory motion, for description of translatory motion of system of particles, it will be easier if we are assuming or if we are considering or if we are introducing the concept of center of mass. Okay. So center of mass means it is the position where the entire mass is assumed to be concentrated. So by knowing that, it will be easier for the calculation or for the description of the translatory motion of the object. Okay. So that is the significance of center of mass. And now we will discuss about center of mass of a two-particle system. Okay, center of mass of a two-particle system. Center of mass of two-particle system. Center of mass of two-particle system. Okay. So here we are considering two particles. X coordinate is y coordinate. Two particles are at positions P1 and P2. And R1 and R2 are the position vectors of these particles. P P1 and P2 are two particles having masses M1 and M2. M1 and M2 are the masses of those particles and their position vectors are R1 and R2. Okay. So the center of mass of the object or center of mass of the system. So the position vector of center of mass is defined as, if R is the position vector, RCM stands for the position vector of center of mass. Position vector of center of mass. And that is defined as position vector of center of mass is equal to M1 R1 plus M2 R2 divided by M1 plus M1 R1 plus M2 R2 divided by M1 plus. So this position vector will be somewhere in between. Depending on the masses of the object, it will be closer to each mass. It varies. Okay. So this is the center of mass. So this will be position vector of center of mass. Okay. M1 R1 plus M2 R2 divided by M1 plus M2. So if x, y is the coordinates, here we can write, if x1, y1 is the coordinate of the first particle and here x2, y2 is the coordinate of the second particle and position vector r, if we are writing it as r is equal to xi plus yj. So this we can write it as xi plus yj is equal to m1 x1i plus y1j plus m2 x2i plus y2j divided by m1 plus m. Or if we are writing x coordinates and y coordinates separately, but we can write x is equal to m1 x1 plus m2 x2 divided by m1 plus m2, and y coordinate can be written as 1 is equal to m1 y1 plus m2 y2 divided by m1 plus m. Okay. So this is the x coordinates and y coordinate. If it is given in position vector, directly we can write it. So if the two masses are equal, one case we can consider, if two masses are equal, what happens? But we can write m1 and m2 are equal, so m can be taken outside. So what you will get, x is equal to x1 plus x2 by 2 and y is equal to y1 plus y2 by 2. Or in terms of position vector, we can write r is equal to r1 plus r2 divided by 2. So if two objects are having same mass, the position vector will be exactly at the midpoint of the line joining those two points. Okay, that is speciality of position vector if those two objects are having same mass. And if they are having different mass, what happens to our position vector will be? The position vector will be closer. Position vector of the center of mass will be closer to the heavier mass. For example, if we are considering hydrogen chloride, HCl. So the position vector will be closer to the chlorine. Okay. If both objects are having same mass O2, so in that case what happens? Both our objects are, if we are considering O2 molecule. So two oxygen atoms are there. So they are having same mass. So position vector of center of mass will be exactly at the midpoint of the line joining of those two vectors. But if one is heavier and another one is lighter, the position vector of the center of mass will be closer to the heavier one. Okay, this is the case of position vector for two particle system. And now we will discuss about the position vector of n particle system. N particle. Center of mass of n particle system. So we are considering n particles and let m1, m2, m3, etc. mn is the masses of the particles. Okay, masses of the particles. And let R1, R2, R3, etc. Rn is the position vector of the particles. And RCM is the, what is that? Position vector of the center of mass. Position vector of the center of mass. Position vector of the center of mass. Then we can write RCM is equal to m1 r1 plus m2 r2 plus m3 r3 plus etc. plus mn rn divided by m1 plus m2 plus m3 plus etc. plus m. Okay. Or we can write it as this, we can write sigma I is equal to 1 to n. Summation, we can use that. Instead of addition, we can use summation. Sigma I is equal to 1 to n. We can write mi ri divided by this m1 plus m2 plus m3 plus plus mn. We can write the total mass of the system. So that we are writing it as m. So here we can mention what is m. M is the total mass of the system. Total mass of the system, which is given by m1 plus m2 plus etc. plus. Okay, this is in vector notation. If we are representing in component form, what we can write, if x, y, z are the coordinates of r1, r2, r3 and so on, we can write x is equal, x coordinate can be written as sigma I is equal to 1 to n mi xi divided by m1 x1 plus m2 x2 plus m3 x3 and m4 x4 like that. We can write sigma I is equal to 1 to n mi xi by m, and here y coordinate we can write sigma I is equal to 1 to n mi yi divided by total mass, and z coordinate can be written as sigma I is equal to 1 to n mi zi divided by 2. Okay, so instead of summation, if it is a continuous object, like a road or something, instead of summation we can use integral symbols. Okay, instead of summation we can write integral x dm. Okay, instead of this we can write if it is continuous object. If it is continuous instead of summation we can write x can be written as sigma I is equal to 1 to, instead of this one I is equal to 1 to n mi xi by m. Instead of that we can write integral x integration symbol can be used. Okay, is it clear? So this is about center of mass of n particle system. So here we have the position vector. If it is given, you can find by using this. If coordinates are given, you can use this for position vector of center of mass of n particle system. Okay, and now we can discuss about the momentum conservation. Momentum conservation and center of mass motion. Momentum conservation and center of mass motion. Okay. So here already we discussed the expression for the position vector of center of mass is given by r is equal to, and we have m1 r1 plus m2 r2 plus etc plus mn rn divided by m1 plus m2 plus m3 capital N plus total mass. Okay. So we can obtain the velocity. How we can get velocity? If we are differentiating this expression with respect to t, we can get the expression for velocity. So differentiating with respect to t. We can write dRCm by dt equal to m1 dr1 by dt plus m2 dr2 by dt plus etc plus mn drn by dt divided by total mass. What is dRCm by dt? That we can write the velocity of the center of mass. So vCm is equal to m1 v1 plus m2 v2 plus etc plus mn vn divided by total mass. Okay, this is the expression for the velocity. Now once again, if you differentiate, what you will get acceleration of the center of mass. So differentiating again, differentiating with respect to t. So dVCm by dt, you can write dVCm by dt equal to m1 into dv1 by dt plus m2 into dv2 by dt plus etc plus mn into dvn by dt divided by total mass. So here actually if you are differentiating, you have to write d by dt of m1 v1. Since mass is constant, that we are taking outside the derivative and we are writing it as dv1 by dt. And what is dVCm by dt? That we can write it as acceleration of the center of mass. So we can write acceleration of the center of mass is equal to m1 acceleration of the first object plus m2 into acceleration of the second object plus m3 into acceleration of the third object plus mn divided by total mass. Or we can write m into acm is equal to m1 a1 plus m2 a2 plus m3 a3 plus etc. plus Mn. So if F1, F2, F3, etc. Fn are the forces acting on the first, second, third and objects respectively. So we can write the net force can be written as force acting on the center of mass can be written as F1 plus F2 plus F3 etc. plus F1 plus F2 plus F3 plus etc. plus F. So if net force is 0, if the net external force is 0, if F net external force is 0, but we can write M into acceleration of center of mass is equal to 0, or we can say that, but we can write velocity of the center of mass is equal to constant. How we can say velocity of the center of mass is constant? How can we say velocity of the center of mass is constant? Because d by dt of mv is equal to 0. So we can say that velocity should remain either constant or it should be 0, then only force will be 0. Okay. And this is about the motion. Okay. So we can say that velocity of the center of mass remains constant if the net external force acting on the system, if it is 0, we can say that velocity of the center of mass is constant. Okay. And now we can find the expression for the momentum conservation. So if F is equal to 0, but we can write this part is 0. So we can write 0 is equal to M1 A1 plus M2 A2 etc. plus Mn A2. Or we can write it as M1 into dV1 by dt plus M2 into dV2 by dt plus etc. Mn into dVn by dt. Instead of accelerating, just like this we can do it. Or we can write it as d by dt of M1 V1 plus d by dt of M2 V2 plus etc. plus d by dt of M1 V2. Is it clear? Or we can write it as d by dt of M1 V1 plus M2 V2 plus etc. plus Mn V2. Okay, up to this it is clear, no? Any doubt? M1 d by dt of M1 V1 plus M2 V2 plus etc. plus Mn V2. So you can see that as d by dt of M1 V1 plus etc. plus that is equal to 0, which means this is constant. No? Derivative of a constant is 0, so we can write M1 V1 plus M2 V2 plus etc. plus Mn Vn is equal to constant, which means momentum is constant. V1 plus V2 plus etc. plus Vn is equal to. So we can say that in the absence of external force, the total linear momentum of the system of particles remains constant. That already we have studied for a single object. In the absence of external force, total momentum of the object remains constant according to Newton's second law. So here also we can say that in the absence of external force, the total linear momentum of the object is constant, and if the external force is 0, we can say that velocity of the center of mass is also constant. Okay, is it clear? So this is about momentum conservation and center of mass motion. Okay. To two bodies of mass 1 kg and 2 kg having position coordinates and 1, 2 and 2, 3 respectively. Have position coordinates. Find the position vector of or find the coordinates of center. Find the coordinates of the center of mass. Find the coordinates of the center. So here how to find the coordinates of the center of mass? Here it is given mass is 1 kg and 2 kg, all those given. So you can use the formula x is equal to m1x1 plus m2x2 divided by m1 plus m2, and y is equal to m1y1 plus m2y2 divided by m1 plus m2. So x1 y1 it is given, x1 y1 is given, what is that 1 2, and x2 y2 is given 2 3, and masses are given m1 and m2, which are those 1 and 2. So we can substitute here m1 mass is 1 into x1, 1 into 1 plus 2 into 2 divided by 1 plus 2 is 3, and here we can write y is equal to m1 1 into 2 plus 2 into 3 divided by 1 plus 2. What you will get? 1 plus 4 by 3, and here we can write it as 2 plus 6 by 3. What you will get? 5 by 3 and 8. So these are the coordinates of the center of mass. Okay, is it clear? So this is the coordinate of the center of mass for two particle system. If it is three particle, also same method you can use, and instead of xy coordinate, if xy z is given, same formula m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3. Okay. Similarly, z coordinate also m1 z1 plus m2 z2 plus m3 z3 divided by m1 plus m2 plus m3 can be calculated. So instead of position vector, instead of coordinates, if position vector is given, what you have to do? Same m1 r1 plus m2 r2 divided by m1 plus m2 if it is two particle system, or if it is three particle system, m1 r1 plus m2 r2 plus m3 r3 divided by m1 plus m2 plus m3. And if velocity is asked to find, what you have to do? m1 v1 plus m2 v2 divided by m1 plus m2 if velocities are given. Okay, is it clear? Show that the center of mass of a uniform rod of mass m and length L lies at the midpoint of the rod. Okay, so we are considering a rod. So its one end, let it be at the origin. So this will be total length will be equal to L. This given. So we have to show that center of mass is position, that coordinate of the center of mass is exactly at the middle point of the. We are assuming that it is lying on the x-axis or x-axis. Okay. So we are considering a small element in this. Small element in this. So what will be the mass of the small element? We can write mass per unit length. Mass per unit length is given by m by length. Mass remains same. So So it is mass is uniformly distributed. So mass per unit length can be written as L by L. So mass of the small element, mass of the small element can be written as small element dx can be written as m by L into mass per unit length into dx. Now what we have to find? We have to find the position vector. So position vector of center of mass or position coordinate of center of mass, that is xcm is equal to what we can find, that is given by here. It is a continuous mass distribution, so we have to write the formula integral x dm divided by integral x dm divided by total mass. And what is dm? Dm is the mass of the small element. And here what is it? Which is the variable? X is the variable, and x varies from 0 to L. So we can write integral 0 to L x dm. Why we have written like this? Because the x varies from initial value 0, final value is L. So we can write integral 0 to L. Dm stands for the mass of the small element, that we can write it as m by L into dx divided by m. So m can be cancelled, L can be taken outside, 1 by L into integral 0 to x dx. So if you integrate, what you will get? You will get it as x square by 2. And if you apply the limit, what you will get? Upper limit minus lower limit. So 1 by L into L square by 2 minus 0. So you will get it as 1. So you can show that it is exactly at the middle. Okay. So this is the way of solving problems related to this. Okay. Sometimes they will find the position vector or find the coordinates of the three masses are there. They are lying on the equilateral triangle. Okay. They are lying on the vertices of the equilateral triangle. Find the coordinates of the center of mass. So if those type of question it is given, if two objects also it is given, it is better you can assume that one object is at the center, one object is at the origin. Okay. So we can draw like this. Position vector. It is an equilateral triangle. So all sides are given A. Masses will be given by m1, m2, m3. Masses will be given. Okay, m1, m2, m3 like that. So better you can consider one object at the origin and another object on the either x direction or y direction accordingly you can find. Okay. Now it is very easy to find what is the what is the coordinate of this one? 0, 0. And what is the coordinate of this? It is A 0. And what is the coordinate of this one? 3 by 2, root 3 by 2. Okay. Now you know all the three coordinates and you can find this. Similarly, if it is of 2, if it is sometimes they will give HCl molecule. So like that, if it is given, what is the position vector or what is the coordinate of the center of mass of the HCl molecule. So in that case also what you can do, H you can assume at the origin and or Cl anyone. Okay. Cl can be assumed at that distance. Okay. Is it clear or vice versa? You can assume. So one it is better you can consider one object to be at the origin and remaining according to the distribution of the mass you can arrange and you can find it. Okay. If it is four particle system, also same way you can find. If it is four particle system, how many can go? One is at origin. If it is not specified, if it is not given, you have to. Otherwise, if it is given accordingly, you have to find. Okay, you can go with this. Okay. So today we discussed about what is meant by center of mass and how to calculate center of mass for different objects and momentum conservation and how to calculate velocity. I hope all of you understood.